Completed all of chapter 2. It's determinants. The vast majority of the problems are really straightforward and some downright easy. And so I figured I would attempt all problems. I did encounter some issues that I'll mention. But other than that, it's just straight cruising. I almost thought of making 2 videos just because of so many problems, but it really fits into one. It's fine. As far as reading is concerned, I read, of course, all of chapter 2, very brief reading. I'll be, of course, throughout the summer trying to get ahead of myself. And so, just to mention today, the actual date of this filming is June 14, late Friday, after work. But I need to be about 3 weeks ahead, somewhere in here, because I would like to put out a video every single Friday. Every single week, without playing games with publishing, such as splitting chapter 2 into 2 videos because there's so much material that I did. Yeah, that's fine. Right, so that's all there is to that. Then I'll show the book. It's all of chapter 2. It's a brief chapter. All about determinants. Of course, finding minors and cofactors. Throughout my career, even after I left physics, and even after I did IT, every now and then, for one reason or another, you'll be surprised how often you need to find out how to invert a matrix. It's really fundamental to anybody who's doing any technical work, in my opinion, at least based on my experience. And so sure enough, the whole business of cofactors and inverting a matrix is something that I have looked up multiple times in the last 20 years. One thing that I really like about this book is the bag of tricks. This book has a great bag of tricks. I had never seen how to do determinants by just multiplying positively the top diagonal columns, the upper triangular part of the matrix, by doing all 3. So you kind of copy 2 columns and then subtracting by the ones that eventually end up in the lower triangular. Great, and it works. It works like a charm. Then evaluating determinants, when you flip 2 rows, you add a minus sign to the whole determinant. You can take out a constant, but it has to be multiplied by every single element along a single row. And then the usual reduction from Gauss elimination that is the same for determinants. Then some theorems that apply to the sum of determinants, but not really in general, only specifically when there's a repeated row. Then Cramer's rule, which actually turns out in some cases does not work well, and the problems cover that, meaning that it's just very hard to do it at Cramer's rule, and you just say, well, how about I just do Gaussian elimination. There it is. This formula, I believe, is very important. The inverse of a matrix using the adjoint, which comes from the cofactors. So it's the cofactor matrix transposed and then divided by the determinant of the matrix, and that's your inverse. And of course, in all these problems, it's always a good idea. I always do it. After I determine the inverse, I multiply by the original matrix to get the identity matrix. Cramer's rule example. And that's it. Yes, and I did the supplementary problems. I did everything. Well, attempted, that is. Attempted is the word that I will use. Because as you will see, there's one problem that really, I tried hard. Let's put it that way. Yeah, so reading, very brief reading compared to, say, analysis, which I have been doing earlier this year. It's mostly just cranking out problems, a lot of mechanics of problems. Making some errors here and there, but otherwise just cranking through all the problems. Yeah. This one is a redo. Even though I don't have the answer for it, I know for a fact that I screwed it up. Too many K's. Too many K's. Yeah. Some geometry. turned into matrices. True and false. Got one wrong there. Yeah, just determinants all over the place. Of course, it's always handy to use a simple matrix A, B, C, D, E, F, A, B, C, D, E, F, G, H, I, just to, especially when in one of the proofs or one of the problems, they're asking about something general about a matrix. That always works. Then you have the general case and you cover everything. Yeah, I got this right. I mean, I knew what the answer was. They did it with the floor function n over 2, but as you flip rows, the number of flips when it's odd, you end up with the same sign, right? I think you do. If you do one flip, yeah. When you have an odd number of rows, you're always going to do a number of flips that yields a negative sign. When you have an even number of rows, since you're always doing them in pairs, you get the same value for the determinant. That's it. Then some more reading. Yeah, in this case I'm doing the reading for the section, and then I go on and I just start cranking out problems. Lots of determinants. And then at some point I hit this problem, 23. This is a really interesting case where you try to do it using Cramer's rule and it becomes a beast. It becomes a beast. And then at some point I said, how about I just do it by Gaussian elimination? Was this the one? I forget if this was the one. No, this is not that problem. I actually got this one correct. Yeah, I got this one correct. Never mind, I'm sorry. I'm talking about a different problem. Oh, here it is, 28. This was the one. I started working it out using Cramer's rule, and it just got nastier and nastier and nastier. Kept trying it, got gigantic numbers. And then I said, how about I just use good old Gaussian elimination? Very easy. Just cranked it out. This is the problem. Yeah. So you try to use Cramer's rule, you basically will never get there. Here and there are some problems that I get wrong. Yeah, I got lazy here and I forgot that it was 3's. When you multiply by 3 and you try the determinant of 3 times that matrix, it's really to the power of n of how many rows. These are square or columns. And so really it should have been 27 times 7, not just 7 times 3. Yeah. And then I got it right on a subsequent problem. Got a true and false wrong there, and another one there. I'll come back to these. I used an example. I thought I had it right. I was surprised that I got it wrong. And then this is the problem that really bested me. I tried it. I did it multiple times, thinking that I got it right, convinced myself that the determinant was 161 because I got it quote-unquote right 3 times out of the 4. Big mistake. It's all wrong. The actual answer is 329 for the determinant. And I never got 329 in all the times that I tried. You can't win them all. And I have to keep going. The diagonals examples, very easy to do. Of course, by this time you've already done it in another method, so you know what the correct answer is. But boy, does this method work. Yeah, and then you want to play with that cofactor matrix for problem number 7 later on, but I had gotten it wrong. I need to revisit it. And then there were some very interesting geometrical problems. I worked them out correctly. This proof, I I have to clean it up, and I missed something. I kept getting the wrong factor somewhere, so I made a mistake. More geometry that worked out. You know, if you do it, if you subtract from in the right order, x1, you subtract x3 from x1, x2 from x1, x2 from x3. If you do it correctly, you get all the signs right. And the matrix that is the area is equal to just calculating the area out by using the area of a trapezoid. Worked out great. And then in this case, I love this problem, 35. I kept looking at it. I tried to solve it, and I got it wrong. And I was like, okay, fine. I'm not even asked to do it anyways. I thought that I could get a 19. It tells you these are 5 large numbers. They're all mod 19 equals 0. They're all divisible by 19. Can you evaluate? Can you show that this matrix, the determinant, is mod 19? Well, I thought, oh, it's really interesting that when you add all these values, you get 19. But then you're never going to get 19 everywhere to guarantee that when you do the matrix, the determinant, you get a factor of 19. And the real answer is so obvious. I even went and factored these out. You don't need to. The fact is, the matrix itself has these large numbers. That's why they list them, because they're actually the entire, all the 5 numbers in a single row. And of course, what do? Well, you multiply by 10,000 the first row, by 1,000 the second row, by 100 third, and by 10 the fourth to the last one, and you get a column that is those numbers. And of course, you don't have to evaluate it. It is mod 19, because when you crank out and you run through this column and you multiply all these determinants, they are all going to have a product of 19 in front. Boom, there you go. And then this last problem, interesting. I didn't really work out in detail, but I know that I think I know the answer is the reason why the determinant is 0 is because this column right here is all zeros. Because when you add all the signs, you get this sum of all the terms in this column times cosine delta plus the sum of the cosines in this column times sine delta. And that is chapter 2.